Hello and welcome. Today I'm going to explain to you two of the three solutions for the problems presented for the second quiz. So here they are. Actually, I am not going to explain the first problem because we already saw it in class. Let's see the problem 2. Prove that any two non-zero elements of a principal ideal domain have a least common multiple. A principal ideal domain is an integral domain in which every ideal is principal, and that means every ideal is generated by a single element. So proof: let R be a principal ideal domain and let A and B be non-zero elements in this ring. We're going to use the following notation. For elements x and y in the ring, we write x bar y to mean that there is an element alpha in the ring such that alpha x equals y. Notice here that when we write this, we can interpret it as saying that y is a multiple of x. So when we write this, we can read it as saying that y is a multiple of x. Also note that it does not matter if we put alpha x or x alpha because we are in a commutative ring. R is an integral domain. Now, by a least common multiple of A and B, we mean an element C in the ring such that it is a multiple of A and B, and further, if there is an element C prime in the ring that is also a multiple of A and B, it follows that C prime is a multiple of C. So, to the proof. Actually, let me comment that this definition captures the idea of the least common multiple that we saw in the integers. So, in order to prove this, we're going to produce an element C with these two properties. First, notice that this intersection of the ideal generated by A and the ideal generated by B is not empty. That happens because the product of these two ideals is contained in the product of the ideal generated by A and R, the whole ring, which is an ideal, because this is containing this. So because ideals absorb products, we see that this product is contained in the ideal generated by A. Similarly, we see that this product of ideals is contained in the ideal generated by B. So this product is contained in both ideals, therefore it is contained in the intersection. Here. Now note that it is clear that this element belongs to this product of ideals, and this element is non-zero because our hypothesis. Therefore, we see that this element, it is in this intersection because of this inclusion, and since it is non-zero, we see that this intersection is non-trivial. Okay, recall that the intersection of ideals is an ideal, so this ideal has to be generated by a single element because R is a PID, that is an integral domain in which every ideal is principal. So let's see that C is a least common multiple of A and B. It is clear that C is in the ideal generated by C, and that is contained in the ideal generated by A because it is clear that this intersection is contained in the ideal generated by A. So this is the ideal generated by C. It follows that C is in here, and therefore it is a multiple of A. Similarly, we can see that because C is contained in the ideal generated by C, which is contained in the ideal generated by B, it follows that C is a multiple of B. So in the notation we saw earlier, we can write it as this. The first condition is verified. Let's see the second one. Suppose that we have an element C prime in the ring that is also a multiple of A and B. Because it is a multiple of A, it is in the ideal generated by A, because the ideal generated by A is the set of all multiples of A. Similarly, C prime is in the ideal generated by B. Therefore, it is in both these ideals. Hence, it is in the intersection. Because this intersection equals the ideal generated by C, it follows that C prime is in this ideal, and therefore it is a multiple of C. And since it is a multiple of C, we are done. We can write it in this way, and therefore the second condition has been verified. Okay, this is the third problem. Let R be an integral domain and suppose that every prime ideal in R is principal. Prove that every ideal of R is principal, that is, that R is a principal ideal domain. Proof. Under the given hypothesis, suppose for the sake of contradiction that the set of all the non-principal ideals of R is non-empty. Note that X is a set ordered by inclusion. What we're gonna do is to use Zorn's lemma to prove that X has a maximal element. Okay, let denote by this an ascending family of non-principal ideals in X, that is a chain in X. So we have that this union is an ideal of R because we have an ascending family, it is a chain. In fact, let's see that this union is an element of X, that is, it is non-principal. And the proof is easy. If it were principal, then it will be generated by a single element, let's say I in R. But by the definition of union, because this element I is in IL, because this element I generates the whole union, it will be in particular in some IL, for some L in the indexing set lambda. Therefore, it follows that this ideal contains the ideal generated by this element. But the ideal generated by this element is precisely this union. And so we have that IL is containing the union, and the union will be containing IL. It follows that we have this equality. But this equality tells us that IL is principal. But the contradiction is that IL is non-principal because we choose the chain in X. So every one of these are non-principal. It follows that this union is in X, that is, it is non-principal. Notice that it's clear that the union contains every ideal in the family. It follows that this union is an element of X, that is an upper bound for the given chain. By Zorn's lemma, it follows that X contains at least one maximal element, let's say M. So this element M is in here, and thus it is non-principal. And by hypothesis, it follows M is not prime, because we stated that every prime ideal in R was principal. Okay, what this means is that there are elements AB in R such that the product AB belongs to M, but A is not in M and B is not in M. Now let us denote by IA the ideal generated by M and A, and IB the ideal generated by M and B. Because we have this proper inclusion, of ideals. That is, the ideal generated by M and A properly contains the ideal generated by M. This ideal by this is precisely IA, and AI. This ideal is the smallest one that contains M, and that is precisely M. So we have that M is properly contained in IA. Similarly, we see that M is contained in IB. Now note that both IA and IB are principal because they strictly contain M, and M is maximal with respect to being non-principal. So it is not properly contained in any other non-principal ideals. That is, both IA and IB have to be principal. In particular, we can write that IA is generated by some element alpha in R. Now define J as the set of all the elements R in R such that multiplying IA by R gives us a set that is contained in M. And note that M is contained in G. That happens because M absorbs products. So if in particular we multiply an element of M by IA, we get a set that is contained in M, as you can read in here. And it's also clear that B is in G, because if we multiply B by IA, we get the ideal generated by this. We get the ideal generated by M and BA. but Bm is clearly contained in M, and Ba equals AB, and that is an element of M because that is what we stated in here. And so we have that J contains both M and the singleton B. Therefore, J contains the ideal generated by this set. By the ideal generated by that set is IB. So notice in here that we have this proper inclusion. M is properly contained in IB and this is contained in J. So again, because M is maximal with respect to being non-principal, it is not properly contained in any other non-principal ideal. It follows that G has to be principal. Okay, so we can write that it is generated by beta for some element beta in R. Further, let's see that IA, J, this product is contained in M. That happens because the elements of this ideal are of the form that you can see here. They are finite sums or products of elements of IA and G. But the elements of IA are multiples of alpha because this ideal is generated by alpha. And the elements of G are multiples of beta because J is generated by beta. So the elements of this ideal are of this form, where all these elements are elements in the ring and n is some positive integer. Notice by the definition of G that this element satisfies this condition. So sk beta multiplied by IA is contained in M by definition of G. So it follows by this that it will multiply sk beta by this element which are in this ideal IA. We have an element of M, and this happens for every k from 1 up to n. And so by adding all those elements, because M is closer under addition, we get that this element is in M. So indeed we see that this inclusion holds. What we have proven up to now is this chain of inclusion. Finally, we produce a contradiction by showing the reversed inclusion in here. That will be a contradiction because the product of principal ideals is principal, and since we will prove the equality, we will be saying that M is principal, which is a contradiction to the fact that M is a non-principal ideal. So let X be an element of M. Because of this inclusion, we have that X is a multiple of alpha, and so we can write that X is equals R alpha for some R in R. Notice also that R is in J, because if we multiply R times IA, we get the ideal generated by this product. By that product is X. So X was an element of M, and thus the ideal generated by X is contained in M. This shows us that X is in this ideal because X is a product of an element of IA, that is alpha, and an element of J, that is R. However, by this and by the arbitrariness of X, we can conclude this equality. And as we said, this is a contradiction because the product of principal ideals is principal, and M is a non-principal ideal because it is in X. This contradiction tells us that our main assumption was false, that is, X is indeed empty. In other words, every ideal of R is principal, and that completes the proof. Now, I've used two facts in the proof that we didn't prove in the class. So here it is, the first fact, and it is actually not difficult to see. So if we have an ascending family of ideals of a ring R, then the union of that family is an ideal over. So let's see that this set satisfies the definition of being an ideal. It is clearly not empty because every one of these ideals are not empty. Now, if we take any two elements A, B in this set, by definition of union, we will have that A is in I alpha, and B is in I beta for some elements alpha beta in the indexing set lambda. Because we have an ascending family of ideals, it follows that either I alpha is contained in I beta or I beta is contained in I alpha. So let us suppose, without loss of generality, that we have this inclusion. The other case is entirely similar. So, because A is in I alpha and B is in I beta, and we say that this inclusion holds, we have that both A and B are in I beta. Since I beta is a subring, because it is an ideal in fact, I minus B is in I beta, and the product AB is in I beta. Hence, because I beta is contained in I, it follows that I minus B and the product AB is in I because of this. So this proves that the whole union is a subring of R. Now let's see that it absorbs products. Indeed, fix some element R in R and let X be an element of this union. We have, by definition of union, that R is in I lambda for some lambda in the indexing set, and thus Rx and Xr are in I lambda, because I lambda absorbs products from left and right. It follows, because of this, that Rx and Xr are in I, and so we conclude that I is an ideal of R. That proves the first fact. The second fact is that the product of principal ideals in a commutative ring is principal. Let R be a commutative ring and consider two principal ideals of R, say generated by X and Y elements of R. It is clear that this element is in this ideal, and so because this singleton is contained in this set, it follows that the ideal generated by this set will be contained in this ideal. That is, we have this. In the other direction, any element of this set is of this form, that is, finite sums of products of elements of this ideal and this ideal. But the elements of this ideal are multiples of X, and the elements of this ideal are multiples of Y. So here we have multiples of X and multiples of Y. We can factor this and get that this sum equals a multiple of xy, and because it is a multiple of xy, it is in the ideal generated by the product sy. So indeed we have that the converse inclusion holds, and therefore the equality holds, and that completes the proof. Thank you so much.